Opportunity to be here. It's a great pleasure. And my talk today will focus on two topics. The first one is in kind of two-dimensional systems, where we are able to control spin-orbit coupling, I would say, in an unprecedented way. And the second part is about spins in quantum dots, where we're looking at the spin relaxation time. So spin-orbit coupling actually is common to both of these topics. And as you know, spin-orbit coupling is of great importance in semiconductor physics and applies to various areas. So here is a picture from a review in Nature Materials from Manchon and collaborators in 2015. And let me just make this point in another way. If we look at the papers on spin-orbit coupling that have spin-orbit coupling in the title, so I guess in 1955, one of the first ones related to solid-state physics with Dresselhaus, looking at systems which don't have inversion symmetry. Then in 1984, Rashba predicted this Rashba effect, which we will talk about a lot today. And then in 1990, Das proposed the spin FET. And there's a big jump, again, even more than after the Rashba paper, and maybe one of the later papers in 2010, the route to Majorana fermions with spin-orbit coupling and superconductors. And if we switch to citations rather than numbers of papers, one can also see it's a very steep increase that seems to be continuing. So spin-orbit coupling, I think it's clear, is a preeminent effect in solid-state physics. It's highly relevant for spintronics, for quantum information, for novel states of matter, such as helical state, topological insulators, Majorana fermions, parafermions, and so on. But it can also be used as a resource, as a technology, because spin-orbit coupling actually provides an internal magnetic field, and this magnetic field can be used to actually, let's say, process quantum information. For example, with electric dipole spin resonance. But it has also disadvantages. In fact, it allows coupling of the spin degree of freedom to a bath. It can cause dephasing and also spin relaxation. So understanding and controlling this type of effect is very important. So here I will focus on gallium arsenide quantum wells as kind of a clean model system to study this. And it has essentially, I'll get into the details of this Rashba and the Dresselhaus type of spin-orbit coupling. So some years ago, Koralek and co-workers found in a very nice experiment what they called the persistent spin helix. And it's a kind of very peculiar, very special case where this Rashba and Dresselhaus effect are exactly of equal strength. In a sense, these two effects cancel and create a situation which is kind of similar to almost not having any spin-orbit coupling left in the system, in the sense that the spin symmetry, SU2 spin symmetry, is restored in the system. However, if we look at the space here, X and Y plane of a two-dimensional electron gas, then we will find that actually these spins are behaving like a wave here. Then in one direction, they're propagating and precessing, while in the other direction, the spin is invariant and is not changing. So this was predicted a few years before by Schliemann, Egges, and Loss in 2003, and with a slightly different twist by Bernavik, Orenstein, and Zhang in 2006. And it was seen in 2009. And one additional benefit that this gives is that actually it protects these spins from dephasing. So in a sense, in this persistent spin helix situation, the spins start to behave ballistically, even though the charges themselves are still diffusing through the system. And that's actually a very useful property of this persistent helix. Actually protects spins from relaxing or from dephasing by over 2 orders of magnitude, depending on how well this tuning can be achieved. And we will see this also in detail depending on how strong the cubic effect of the Dresselhaus is. So far this has been realized in kind of isolated points, which were kind of very hard to actually obtain in samples. And today I will show you how to actually make use of this in a sense of developing this as a technology that could be useful for spintronics and potentially for quantum information. So this new concept that I would like to introduce is the so-called, what we termed the stretchable persistent spin helix. If you had a way, let's say with two different gate voltages in your sample, to actually independently control both this Rashba effect with the coefficient alpha and independently the Dresselhaus effect with the coefficient beta, then you could go to such a way that you actually change alpha and beta while keeping them locked together at equal strength. So if you did that, then you could basically change the pitch of this helix. You could change the length scale over which, let's say, a 2 pi rotation in the propagating direction, in the precessing direction occurs. So here we put some parameters that are extracted from the data. This is 5 milli-eV angstrom in these units, and it corresponds to a precession length of about 3.5 microns in the strong spin orbit direction for the spin. If we now tune together alpha equals beta from 5 down to 4, then actually what will happen is this precession length becomes longer, this effect becomes weaker by about 25%, and so now we have changed this. So if we look at this, if you look at the spin here, for example, at around 5 microns, we see that the spin at this location actually rotates its spin direction by about 90 degrees. And okay, you can say this has been done before. You can change the spin precession length just with the gate voltage. But what's new here is for all of this operation, because we are doing this while remaining inside this persistent spin helix state, we're benefiting from this protection of relaxation. So the spins don't dephase and basically lose their polarization as we do this experiment. So ultimately this will be limited by the cubic effect, and this corresponds to, for the present samples, to diffusion lengths of around 10 to 25 microns. So these are quite long distances, correspond to several 2 pi rotations, and could possibly enable kind of long-distance spin communication, for example, between a spin qubit, a quantum dot at one location, to kind of a further remote other qubit. This is all available on the archive, was submitted a month and a half ago in this paper. So let me go into a little bit more the details after introducing the concept here. So the Rashba term is due to the absence of inversion symmetry in the quantum well. And basically, if you have a top gate, which you can apply a voltage to, and the bottom gate, in this structure, the quantum well is somewhere in between, maybe something like 80 nanometers below the surface, then by fine-tuning these voltages, we can, for example, keep the charge carrier density inside the quantum well constant while tilting the potential, changing the electric field in the quantum well. So we can kind of tune it to become symmetric, effectively making the Rashba effect go away, making alpha 0, or we can tilt it in the other direction and even changing sign of this effect. And if you have not only a top gate or not only a bottom gate, but actually both, what is beneficial is you can do this independent of the density. So basically you can tune this Rashba coefficient separately from the density. If you look at this, what this means, what does the effective magnetic field look like in the plane of the 2D gas, so this is the x direction and the y direction, then this looks like a kind of a tangential field that goes around here, the Fermi circle, and one can decompose this and rewrite this in terms of an angular variable, and it shows up here only as first harmonics. I'm saying this because the Dresselhaus term will have also different contributions. So this kind of top and back gate technique is not very new, but it's actually a little bit difficult to do, because when you make the contact to the 2D gas, it's very easy. This is overall only maybe a micron or two from the surface, so it's very easy to actually short circuit the 2 deck with the back gate in a contact, and that would be very bad for the experiments. One has to kind of optimize the parameters to get the ohmic contacts to make a contact to the 2D gas and not a short circuit to the back gate, which is then contacted separately. So here we're following a kind of a trick that's been developed many years ago by Maranowski and co-workers to grow this barrier here at low temperatures, which causes defects to kind of pin the Fermi energy in mid-gap and actually allows very low leakage currents and very large ranges for tuning these gate voltages. Then with the top gate here on the vertical axis and the bottom gate on the horizontal axis, we can change density, and that also affects the mobility. And we can basically measure these contours of constant density, which nicely agree with a very simple plate capacitor model, which depends on the lever arm given by the distance of the surface gate to the 2D gas and the 2D gas to the back gate. So now turning to the other term, the Dresselhaus term is a general term in crystals in 3,5 compounds, which don't have bulk inversion symmetry. And it's actually a 3D term, so and it shows up with the K in a cubic variation. For example, here's a term that couples sigma x to kx and ky squared, and then there is a corresponding term with y, and x squared, plus a cyclical permutation. So there's overall 6 terms that show up here. Now, when you have a 2D electron gas, then one can actually quantize this and kind of project these terms into the lowest subband and take advantage of the fact that in the z direction electrons aren't going anywhere, they're localized in the quantum well, but the expectation value of kz squared is still not 0. And if one does that, and again rewrites the Hamiltonian in terms of this angular variable, theta, then it turns out that there is 2 terms. One is kind of a first harmonic, and the other one is a third harmonic term, which comes from the original cubic nature of the effect. And the coefficients are now effective coefficients, which for this first harmonic term has 2 components. One here is given by the width of the quantum well, and the other term is given by the density. And actually it gets subtracted here, while this third harmonic, it has the same coefficient beta 3, which shows up here also in the first component. So this decomposition is nothing new, but it's actually kind of surprising that in all these years, in no experiment was it demonstrated that actually this effective Dresselhaus coefficient beta, which is the coefficient that shows up in all these Dresselhaus terms that appear in Hamiltonians and so on, it has never been demonstrated really to be tunable by the density. So we take advantage of this, and actually through tuning the density, which we can do independent of the Rashba effect, as I've said just a slide ago, we can actually control with the gate voltage the strength of this effective Dresselhaus term. So if we now look at these 2 terms, we can also plot the Dresselhaus term. It has a slightly different texture compared to the Rashba one, and if we basically add them up together, then depending on how strong the Rashba effect is relative to the Dresselhaus effect, and now we assume that by changing the top and back gate voltages here, symbolically just written as V gate, in such a way that we start matching the 2, then when they're matched, the picture looks like this, where basically independent of which direction here in the 2D plane an electron is traveling, it will always feel an internal spin-orbit field which is pointing in the same direction. So that's what we refer to as a uniaxial spin-orbit field, and this has the effects that I described earlier. Basically, it effectively restores the spin symmetry in the plane and makes the system behave in many ways as if there wasn't any spin-orbit coupling. So what this does, to give one example, if we have some kind of diffusive trajectory of some charge, then as it goes through the system, the spin is rotating. But when we're in this persistent spin helix state, then basically only the projection of this trajectory along the strong spin-orbit axis here plays a role, and no matter which path an electron takes, let's say from A to B here, it always accumulates exactly the same spin precession. So this is the reason why this basically protects the spins from dephasing. Yes. Right now I just neglect it, and in the experiment I will show that it's kind of small, although as you will see it depends on the density. For very large densities it can become appreciable. But this, it's a good point, this is neglecting the cubic, the third harmonic, which actually breaks the symmetry and will make this look, slightly different. I mean, I think I had a picture of the third harmonic here somewhere like this. So this gets added, It turns out to be the main detrimental effect. There's a couple of other candidates that in principle could also break the symmetry, but at least in these kinds of semiconductor quantum wells, they turn out to be very small. Right. So as a further consequence, actually, this means that the trajectories that contribute to corrections of quantum corrections of conductivity will basically become spin independent and in a sense destroy weak anti-localization and just go back to the situation as if it was without spin. So this is a nice detector. The absence of weak anti-localization we can use as a very sensitive detector to tell us whether we have reached this persistent spin helix state in any given configuration of parameters. So here's an experiment that we do. So in this top gate, back gate plane, we can go along a contour of constant density and actually change here the electric field across the quantum well. So going along this path here will tune the Rashba effect while more or less keeping constant, in this particular case, the Dresselhaus term. And here's the data for these 1, 2, 3, 4 through 7 different points. And you see here at point 1, we see some kind of anti-localized peak here. So this is plotting the change of the conductance with respect to conductance at zero field, and these traces are offset for clarity. This is magnetic field here. This is vertical magnetic field applied perpendicular to the 2D plane. And we see here there's a maximum of conductance, so that's weak anti-localized type of behavior. But when we go here to curve 4 or 5 or so, then we see that there is actually a very pronounced minimum of conductance. And then if we go further and make the change the Rashba term even more, then it goes back to this kind of anti-localized behavior. So from just looking at these graphs, and we can do a more sophisticated analysis, but even just from looking at it, you can now point somewhere between 4 and 5 in gate voltage space here and determine that in that range of parameters for this density of 4.5, we actually generate the spin orbit parameters to support the persistent spin helix state. So this is actually a very sensitive detector for this state. In fact, people are maybe also familiar with this kind of Shubnikov-de Haas measurements to study spin orbit effects, but it turns out this is vastly less sensitive. So if you look at these, this is the data here from one of these points here, maybe I think it's point 1, and you don't see any beating in this. I mean, in fact, you'd have to go to, I think, more than 100 oscillations to start seeing the beating. I mean, in materials with stronger spin orbit coupling, this could be visible, for example, in indium arsenide. You could possibly see a signal, but not for this gallium arsenide wells. So actually, this quantum interference effect of weak anti-localization and weak localization is very, very sensitive detector of these kind of spin precessions that are taking place in the sample. So now, using this type of methodology, as I just showed you, we can actually do this not only for this density 4.5 or whichever it was, we can do this for various densities in the wafer and actually determine kind of a path throughout this top gate, back gate parameter space where we will always match alpha equals beta as long as we're staying on this path. And we can do this also for different wafers. We can change the width of the quantum well. I think this blue one was a quantum well of width 9.3 nanometers. We can repeat this for some thinner or thicker quantum wells, and these traces get shifted up and down. But this actually allows us now to extract some important parameters. So basically using a numerical simulation to calculate for us this expectation value, basically the width of the quantum well, as well as giving us the Rashba coefficient, then we can extract this coefficient gamma from basically matching these data. If we're changing this Dresselhaus coefficient, then basically these lines are moving up and down depending on the strength of gamma. And these simulations were actually done by Zhang Fu and Carlos Eges, and they've described how to do this already in an earlier paper. And basically they simulate this Rashba term, which has 3 components. One is from the kind of walls of the quantum well, the structure of it, and depends on the kind of band offsets that one gets, as well as the Hartree term and some gate and doping term, which here goes into overall this Rashba coupling strength. And yeah, this this can all be tuned with the gate-induced electric field. So it's given by basically the difference of the top and back gate voltage normalized here with the respective lever arms. So if we now look at a case where we're going along one of these paths, where we are, as long as we're on the path in the persistent spin helix state, then we can now look at the simulated values to see how we're actually changing this Rashba and Dresselhaus coefficients. And it turns out, if we're going from some kind of density close to 2 to a density up to about 7 times 10 to the 11 per square centimeter, then we're actually reducing alpha from about 5 to 4, and the same is happening to beta. So this corresponds to this movie that I showed you in the beginning, where we're actually changing 2 times alpha, or it's the sum of alpha and beta, or 2 times one of them, from about 8 to 10 millielectron volts angstrom, corresponding to this kind of spin precession length for completing a 2 pi precession from 4.4 to about 3.5 microns. So put another way, if we're propagating for 5 microns, then this can actually give us a pi half rotation change as we're changing from here 4 to 10 milli eV angstrom. Now, I don't show the details so much here, but the simulation actually in this range here also gives us what the cubic component, kind of detrimental component that breaks the symmetry is. And this changes from maybe 0.5 or 0.4 in these same units, just above slightly 1. And one can put in what kind of lifetimes this gives, or what kind of effective lengths, spin diffusion length, and this corresponds to somewhere from 25 for the lowest density when beta 3 is smallest to about 8 microns for the largest value. So that kind of limits the protective power of the spin helix states due to this cubic effect. Now, just to give you an idea, if we're not matching alpha equals beta, let's say we have a difference between alpha and beta of about 5 milli eV angstrom, then that corresponds to a decay time of only 5 picoseconds, compared to even nanoseconds with the protection of the spin helix state, and effective lengths of only 2 microns. So this is actually a fairly large effect here. If we look at these lifetimes, we're looking at 1 to even more, two orders of magnitude of improvement of the lifetime. Right, I've showed this already. Okay, so we can also, by looking at these quantum transport curves, we can also identify the regime when actually, for example, alpha is equal to 0, or we can also look at, I will skip the details here, we can go to higher densities, and even when we're making alpha equals beta, we will still get a weakly anti-localized signal here. This is also for different points along some constant density contour, and basically by analyzing this peak, one can again extract the strength of the cubic term and get values which agree fairly well with the simulation. So when it's strong enough, then the symmetry is broken, and we do still get anti-localization even when the linear terms are matched. So that's then the effect of the cubic term. Okay, so let me wrap up this first part here actually by pointing out that there is not really a theory of all these quantum corrections. I mean, we have done these simulations which kind of calculated the spin orbit parameters, but to actually calculate the corrections to conductivity, that's a difficult problem. It's an old problem that has been around for many years. I mean, people like Hikami, Larkin, Nagaoka already in the early 80s, late 70s worked out these kind of formulas. But it turns out there's many of these theories, but none of them actually are applicable to the case of having both Rashba and Dresselhaus terms, especially Dresselhaus, the linear term, as well as the cubic term. And it's genuinely a hard problem to solve. And we tried to, together working with Catalina Marinescu from Clemson University, we tried to kind of come up with a new theory using the old formalism, which is particularly suitable for this persistent spin helix regime. So the theory gives good results when alpha is similar to beta and the cubic term is not very strong. And it similarly works when one of them is 0, and it works also with magnetic field. So we include actually the Rashba and both linear and cubic Dresselhaus terms, and then can solve this problem. And actually, what comes out is a formula that has exactly the same structure as this old Hikami-Larkin-Nagaoka formula, but it has been reparameterized. So we get the parameter which we now call HSO2, which depends only on the difference of alpha and beta, and we get this HSO3, which is a term that corresponds to the third harmonics, this cubic term that breaks the symmetry. And with this, one can actually then calculate these quantum corrections to the conductivity. Well, H phi is another magnetic field related to the coherence time of the system. The fusion constant goes in, and these psi's here are the usual digamma functions that show up here. So, yes, sure. Yes, you can have either one. So this formalism works for both alpha equals beta or alpha equals minus beta. Now here it's written for alpha and beta having the same sign, but you can recast it in a better way. Yeah, it's symmetric around that. It doesn't matter. That it works for both cases. I mean, in this formulation it doesn't, but you just have to put the... Right, right. Right, so now we can basically do a similar game, but it's a little bit difficult to fit this, so we have to do kind of a clever way to extract the different parameters. I mean, the different parameters are well, we'll see, it'll come up. So we'll first find the point where alpha is close to beta in the same way, basically picking the curve here that looks the least anti-localized, and then saying that at that point we're close to alpha equals beta, and so this HSO2 field, which shows up here in the equations, is actually equal to 0. And then at that point we actually can fit, using the formula, extracting only this HSO3 and H phi, the coherence parameter. And then once that's done, then we can actually now go away from alpha equals beta and perform fits for all of these curves, but at this point, since we have no reason to assume that neither the coherence time nor this HSO3, the cubic part, is going to depend on the electric field that's applied across the quantum well. Remember, this is a contour of constant density, so we're going to keep these parameters fixed and only extract HSO2 at this point. So it's a fit with only one additional parameter. We keep the other ones fixed. And this actually works fairly well, and we can do this and kind of plot it. And we can again repeat this for various densities. Here this is densities from 7 to 9. And parameterize this different HSO fields. So we can parameterize this HSO2 as having a component which is dependent on the electric field, with the prefactor here as a fit parameter, a constant offset. This constant offset could be due to built-in doping, depending whether the wafer is symmetrically or not symmetrically, or how it is actually doped. And then there is this additional term from this beta 3 part here in the coefficient beta. So with this parameterization, actually we end up having 3 fit parameters. This goes in as a single fit parameter, this coefficient alpha 1 and this coefficient gamma. And we basically fit all of these densities at the same time, while already keeping fixed this HSO3 value, and ultimately can actually extract the parameters. And now we can compare them to the simulations that we did before. And actually it gives fairly nice agreement. So this offset depends very much on the wafer, but this coefficient alpha 1 that is going to scale with the electric field, that's going to change the Rashba parameter with electric field, it actually comes out somewhere close to 10 in the from the fits to the experiment, and it's close to 9 from the simulation. So it's fairly good agreement. And also for this Dresselhaus parameter gamma, we get 11 point something, 0.2 here with some error bar, whereas we got 11.6 from the other method. So again, this is kind of decent agreement. And actually, this I should have mentioned earlier, this parameter gamma is quite controversial. I mean, first of all, when it's calculated in different theories, one gets quite different results. I mean, ranging from just maybe 2 or 3 up to 50. And also the experiments, especially the earlier ones, were kind of scattered all over the place. So this is now, I would say, a more reliable way to measure this gamma, and it also agrees with a couple of optical experiments which also come out around 10. So this seems to be a more reliable way to extract this. So let me actually conclude this first part by acknowledging all the collaborators. So the measurements and sample fabrication were done in Basel by my students Permin and Florian, and we have a very good collaboration with Zhang Fu and Carlos Eges in Sao Paulo, and Catalina Marinescu at the Clemson University. And very good wafers were designed and grown by Sean Mack at UCSB and David Oshalom, who is now in Chicago. So let me summarize this part. We introduce a new concept, what I call the stretchable persistent spin helix. We can basically gate tune the pitch of this helix, and this is a kind of technologically relevant concept because it allows us to manipulate the spins in a regime where the decay is very weak. It's basically only limited by this cubic effect, which gives spin diffusion lengths of 10 to 25 microns. And in a kind of later part, we put forth a new theory of quantum corrections to conductivity, which are applicable in the spin helix regime, and kind of use this theory to fit to the data and get actually good agreement with the numerical simulations. So as an outlook, we would like to use this type of wafers with top and back gates as a platform for performing kind of custom tailored spin orbit experiments. I mean, this allows us to basically independently tune the most of the relevant spin orbit parameters, and I think this could be useful for quantum wires, quantum dots, qubits, and yeah, it would be nice also to combine this technique with the optical measurements to get additional information about these kind of states. So I don't know if you want to do questions now, or should I just continue with the second part? Yeah?
About this. So any question?
So I'm trying to understand the spin helix. In particular, I'm interested in what is the spin density of this helix, like the spatial spin density.
Right. So in actual experiment, you would probably inject some spin polarization, and then, for example, you could watch how it diffuses through the system, or you could drive it with an electric field. And basically, normally one would have kind of the Diakonov-Perel relaxation. So every time the momentum is changed, also this internal magnetic field is changed, around which the electron spin is precessing. And so in the normal situation, this leads to a spin which is dependent on the path. So if you go from, diffuse in some way from A to B, then it depends on which path has been taken. But if you're actually, if the sample is in this persistent spin helix regime, then because irrespective of which direction the electron is moving in the plane, it's always a field which is pointing in the same direction. The internal magnetic field always points in the same direction. So the spins kind of are winding and unwinding, and in the end, it doesn't matter anymore which path has been taken. So that's the way this thing works. I don't know if that answers your question.
No. So I understood that part. So you have an electron moving, and it kind of doesn't matter which path it takes for determining what kind of direction it will point in the end. But is this spin helix, is that now a static magnetic texture in the 2-deck? Is there a magnetization?
Well, okay, so in our experiments there is no magnetization that's injected. We just basically use the unpolarized electrons to do these quantum transport measurements, which give us these quantum corrections. But what we are able to do is we are extracting what the spin orbit parameters are, and so if one were to inject a spin polarization, given those parameters, then this would result. So if one were, for example, to use a quantum point contact to inject spin, you have to apply some large magnetic field, get the Zeeman splitting, and then inject the spin. Then in addition to the external field, these internal fields, which are actually also of order of several Teslas, then the spins would then precess around this internal field, well, the sum of the internal and the external field. And you could put some another QPC as a detector at some other place and kind of detect the spin polarization, for example, if you're looking for an example.
That's why. No, I just missed. I didn't understand how you measure the persistency of the spin helix, like the lifetime of the spin helix.
Right. So here it's not measured. We basically extract the cubic term, and when the Rashba and Dresselhaus effect are matched, then we can calculate it. Now, in some of the optics experiments, they can actually measure it. They have they do pulse probe spectroscopy, and they see that they can measure how fast they actually excite this helix, and then they can measure how fast it decays. And that agrees very well with these types of calculations.
But you cannot measure it directly
No.
from. Okay.
No.
So how does the picture of the spin helix change if you now include another kind of spin relaxation mechanism like Elliott effect?
Right. So if there is some additional spin relaxation, then it would start just exponentially damping. Well, I'm assuming this would be exponential. It would basically damp this spin wave on the length scale of that particular mechanism which you're adding to the system. Elliott-Jaffet actually is very small in these systems, but yeah, in principle there could be some other coupling to some bath.
Any further question about this topic? All right, I guess we can move on. Just one last point. It is actually a texture if you have two of them orthogonal, one going like this and the other going like that. If you manage to excite that, that forms a skirmion lattice in Rio space on top of the two-dimensional electron gas. Yeah.
Yes.
Yeah.
Yes. Yes.
That's right. No,
No, no, it is.
It is a spatial texture.
It's just
Sure.
that in our experiments, we don't inject any spins. It's just a 2D gas. You know, there's no polarizer, there's no analyzer. No,
No, not in
No.
the experiment.
no, but we just. Yes,
Oh,
you
yeah.
could measure it.
It's not
So
measuring
absolutely,
it.
that's
It's
what I
not
was
even
saying.
exciting it. Yeah, that's right.
If you shine circularly polarized light on the sample,
Yeah.
you create spin polarization, then it will create this wave, exactly the way it's shown. And people have done this, like John Solis at IBM in Zurich. They have done exactly this and actually spatially imaged this spin helix.
It's not a ground state property. So the 2DAG will never, if it lower the temperature, will do whatever, it is not going to go into that state because it's not a ground state. It could have some ferromagnetic transition, but it would not be like that. Actually, Catalina Marinescu did this calculation when we were in Santa Barbara because she thought it was actually a ground state property. You may remember some discussion we had. And it's not a ground state property. It's not a spin density wave. It looks like it, but it has to be excited. It's an excitation. So it's not the same in the sense that it's not it would be still an excitation. So you just have to create two of them perpendicular to each other, and the texture looks exactly like a skirmion lattice. But then if you wait long enough, it's just going to disappear because of the cubic term. Right?
But it's completely measurable. I mean, it has been measured. The original experiment actually created a grating in space already to start with, where they had, spin up, spin down, alternating along some axis. And that also works well. So that's how they first did the first experiment by Koralek, I think in 2009.
Koralek,
they created this spin grating, which then they watched decay over time. It's measurable. All right, so let me come to the second part, and basically I will skip some of the slides to time, but let me just introduce these kind of surface gate defined quantum dots here, where we have these gates that can be used to shape the potential. And of course this was proposed many years ago as a qubit, and it's particularly attractive because it does carry the potential for scaling. So looking at spin decoupling techniques, CPMG or many other techniques actually have extended T2 stars, which were first in the range of nanoseconds, now well above milliseconds. And well, fundamentally, the limit is T2. So T2 is 2 times T1, this was shown. And so it's always a question of what actually limits the spin relaxation time, T1, in such a system. On top of that, it can also limit the readout fidelity, because for the readout you have to wait some finite amount of time to actually be able to read the spin state, and if that starts to become long, then T1 could play a role. Or if you want to reset or basically initialize the qubit, then also T1 could be a resource, and it could be useful to have it fast. In some situations, be able to switch it to slow at a later state. So in this second part, the next 10 minutes or so, I will basically show you some physics of this fundamental T1 type of process of a single electron in a quantum dot. So we have a charge sensor on the side here. Current is flowing through this dot, and it can be used to detect the presence or absence of an electron here in the central part. So this 2D electron gases, they are from Gossard at Santa Barbara, and these layouts were inspired by Charlie Marcus's group. So I think I'm going to skip all of this. Sorry about that. This is where I will continue. So what actually sets the spin relaxation time? Well, if we apply a field and then look at these spin states, and then in that case, we have to somehow carry away the angular momentum. And if these spin states are pure, then that's actually very difficult. But if they're mixed, for example, by spin-orbit coupling, if the ground state is not a pure spin up, but it contains some, although small, admixture of spin down, then this can start to relax because of the excited state is also then mixed, and then basically it already has a component of spin up, and the corresponding energy just needs to be given to another bath. This other bath could be the phonons in the wafer, it could also be photons or some other bath. It turns out, and this has been shown, has been first predicted theoretically many years ago and then shown in a long range of experiments, that this phonon emission due to mixing of the spins by spin-orbit coupling is the predominant effect of spin relaxation. So in one of my experiments back at MIT in 2008, we've demonstrated this fifth power of magnetic field dependence, which is a prediction that comes out of theory, and we found T1 times as long as 1 second at low fields. And so the physics of that is actually very similar to what I was saying before. Basically, this Rashba and Dresselhaus terms, they are setting the spin relaxation rate in the following way. So if we rotate this Hamiltonian into the coordinate system of the quantum dot, where we have the 1, 1, 0 direction here in the horizontal axis and the 1, 1 bar O direction in the vertical axis, then actually we get two terms. If we apply the magnetic field here in the vertical direction along y, then this term has a sigma y, so it's actually diagonal in this term, and it will not cause relaxation. The first term, however, has sigma x, and so it will cause rotations and actually relaxation. And so this term, for the particular case, when the field is applied along the y direction, will set the spin relaxation. So in this case, theory predicts b to the fifth dependence with this lambda minus, which is the kind of length corresponding to beta minus alpha, and it shows up as a square, together with the orbital energy of the y state. You see the Hamiltonian here has a momentum in the y direction, so the orbital, the state of the orbital here plays an important role also in the way these states are mixed. So if one now looks at the anisotropy, so that means that the dependence on the direction of the magnetic field applied in the plane of the spin relaxation rate, then one finds basically that there's two factors. There's a factor due to spin-orbit coupling, And if we change the direction, then we get, instead of beta minus alpha, we get beta plus alpha, and we get this factor, which shows up squared, and we get the ratio of the excited states in the x and the y direction, which also appears. So, yes, question. I didn't calculate this. I'm citing some papers here. They were on the first slide. This is Golovac and Los Koitsky in 2004, and Koitsky and Nazarov, they had some papers already before where they were looking at this. I mean, the physics of this is basically Fermi's golden rule, density of states of the phonons, so it matters whether it's piezoelectric or deformation potential phonons, but I have to refer you to the details. I mean, how to get b to the 5, you have to count the powers. I'm sorry, I mean, phonon density of states, I think, gives you a b to the 2, but then there is more powers. We can look at the papers, I can show you, but I cannot explain it to you right now, right here. Okay, so you see from this that in order to actually learn something here and understand this, we need to get a handle on both the quantum dot orbitals as well as the spin-orbit coupling, Rashba and Dresselhaus parameters. And so to actually do this, we need to develop a technique to actually measure and characterize the orbitals of the quantum dot in a good way. And so in this particular setup, we use a rotator, a piezoelectric rotator, which is holding the sample. This is a socket, and the chip carrier goes inside that. This whole thing gets cooled to about an electron temperature of 60 millikelvin, and we can rotate this inside a large magnetic field. So this is a magnet that goes up to 14 Tesla, and we can rotate this. Now, when it's rotating, it heats up the sample a lot, but if you wait another hour or so, then you can measure again at low temperature. And we use a charge sensor here. This is another quantum dot adjacent to the main dot, which is in Coulomb blockade. You see a range of Coulomb blockade peaks. You pick a nice one. You go on the point of largest change of conductivity that's around, and then you can basically measure this whether an electron is on or off the quantum dot. So to measure the excited states, we have kind of a problem, which is the bandwidth of this charge sensor is limited. It's around 30 kilohertz in our system, but the tunneling rates of these excited states, they're quite high. So what we use actually is pulse gate spectroscopy with kind of sub-microsecond pulses to get a handle of these excited states. So we first empty the quantum dot, so we pulse here, we change this pulse gate voltage, it's one of these gate voltages on the dot, to bring both the excited and ground orbital states of the dot above the chemical potential, and we wait a certain time for the dot to empty out. This could be, a few hundred microseconds or a few milliseconds, and then we charge the dot, and it turns out that it almost always tunnels into the excited state, because the excited states, because they're more extended orbitals, they have better overlap with the reservoirs, and so they have much higher tunneling rates. So when the ground state tunneling rate is, let's say, 100 hertz, it could easily be that this excited state tunneling rate is already a megahertz, just because of this overlap type of effect. It's exponentially sensitive. And then we read out whether or not an electron has tunneled onto the dot. And this is done in some clever way. We basically, when we pulse these things around, we have to compensate the charge sensor to stay on this sharpest point of highest sensitivity. And with this we get the kind of tunneling rates that we can detect of 30 kilohertz, and we use some sophisticated equipment to do that. So, but now with this, we can basically detect, by measuring the tunneling on rate, we can see where the excited states, the orbitals of this quantum dot are. And so here, this is pulsing in energy, the system lower and lower. We see one excited state here at 2 millivolt, another one at 3 millivolt, and another one close to 4 millivolts here. So these are different excited states that can tell us about the orbital confinement of the quantum dot. So now, using the gate voltages of the system, we can basically start tuning and shaping the electrons in this dot. Let's assume, just for fun, that at this left point in this kind of gate voltage space, the CP, we're actually changing a whole set of different gates, not only one. The dot is kind of elongated just because the original shape is kind of elongated, but we will confirm this shortly. So now, as we're going from left to right here, we're actually decreasing this voltage, and it corresponds to kind of pushing the dot together with these two walls while we're making the space larger for the electron in the vertical direction. So that's kind of the change of shape that we're trying to achieve here. And then as we're doing this, as we're going from left to right, one of these excited states is moving up in energy and the other one is moving down. At some point, they're basically becoming nearly equal and becomes hard to measure when they're exactly equal. And then they separate again and go on out on the other side. And so if we look at this deformation, we can actually, by changing these gate voltages here over a few hundred millivolts, we can change from a dot that's elongated horizontally to a circular dot to a dot that's elongated vertically. And this is going to turn out very important because, as you've seen, for this kind of spin relaxation physics, this is one of the predominant terms. Now, how do we really know that this is true? Well, we know from the gate voltages which one is large in which direction, so that gives us some indication. But now, with this large in-plane field, we can kind of develop a new kind of spectroscopy where we actually apply here a large magnetic field in the plane of the 2-DEC in different directions. So this first experiment, we apply it in the x direction. That's here in this horizontal direction. And looking at the two lowest excited states, we see that one state, the green one here, is basically not changing its energy at all. The other state is going down from about 2.6 millivolt and is reaching close to 2 millivolts at 14 Tesla. So what does this tell us about this magnetic field, about this orbital? Well, if you apply the magnetic field along a certain direction, then if there is an orbital along the same direction, then the field will have no effect. The magnetic field has effect on things that are orthogonal to it, right? It acts like a vector product. So this must be an x state, and the blue one must be the y state. And that corresponds, that's in agreement with what I've told you earlier before. And now we can rotate the chip by 90 degrees and apply the magnetic field in the y direction, and then it has to be exactly reversed if what I'm saying is true. And so indeed, now the blue state remains unchanged within some error, experimental error here, while the green state is going down. And so again, we can say that the one that's not changing at all is now the one in the y direction, and this one is the one in the x direction, as we've had it before. We can also do, at the fixed magnetic field, we can rotate the sample and see how these excited states are changing, and basically we can make a kind of sophisticated model, which is done by Peter Stano at Riken. And from this type of data, we can not only get the x and y confinements, which we already had, but we can also get the z confinement, and we can get the angle with which the dot is sitting in the 2-DEC. So this allows us to quite precisely, basically by looking at these maxima, to get not only the shape, but also the orientation of this quantum dot with respect to the crystal axis and the magnetic field. So this is very useful, and basically now we are equipped to measure T1 in this system. So how do we do this? It's quite simple. We first ionize the dot, then we pulse the levels. This is now the Zeeman splitting, so we're now applying some magnetic field that will give lift the spin degeneracy here and give a Zeeman splitting of delta. Then we're charging the quantum dot, and this electron can either tunnel into the spin excited or the spin ground state, and then we wait for some time. If it's in the spin ground state, then it'll probably just stay there because this Zeeman splitting is larger than temperature. But if it's in the spin excited state, depending on how long we wait, it will relax or it might not. Finally, we read out the spin by doing kind of a spin to charge conversion. If the electron is in the excited state, it will tunnel off. If it's in the ground state, it will stay. So if we have a tunnel off event, we know it was still not relaxed. So I'm going to skip these details, but basically by doing this kind of analysis, we can plot the ratio or the probability of having an excited spin event as a function of the waiting time. And first we see basically the tunneling in rate, and then finally here at the long waiting time end, the longer we wait, the less likely it becomes that we have a spin excited event. And so from this behavior, we can get the spin relaxation times or rates. And this works very well. So now, for example, at some fixed field, we can rotate the quantum dot and measure what the spin relaxation rate is here as a function of the direction in which we apply the magnetic field. And we find there is a pretty strong dependence, actually it's about the factor of 15, by which the spin relaxation rate is changing. And this already allows us, since we know what the orbitals are in the way with this model that I explained to you, this allows us to say that the ratio of alpha and beta is around 2, or 1 over 2. This is cannot be distinguished at this point. Note also that the Delft group has done a similar experiment a couple years earlier. But we now know the orbitals, so we can make definite statements about the spin orbit strength. Now what's interesting is we repeat this experiment at lower magnetic field, and the prediction of the spin orbit theory would be that we still have this factor of 15. That's actually turns out to be field independent. But it turns out in the experiment at this lower field that in these minima, where the spin relaxation rates become the smallest, this starts to deviate from the theory. And actually we get higher spin relaxation rates than what's predicted. And so if we look at this now, if we fix the angle and take the magnetic field along the y direction, which is the direction along this minimum of the spin relaxation rate, then we see what this looks like. So this is magnetic field from half a Tesla to 14 Tesla, and at high field this still follows this b to the 5 from spin orbit coupling and phonons. But at low field, below maybe 2 Tesla or so, in this slow direction, it starts to behave like a weaker power, and it seems to be kind of consistent with b to the 3. And this actually is a new mechanism for actually mixing the spins. So it's no longer spin orbit coupling, but this is a mechanism that was predicted by Siggy Erlingsson and Julian Nazarov in about 2002. Actually, hyperfine coupling creates kind of random Overhauser fields, and the spins start mixing because of these Overhauser fields. And this turns out to give a b to the 3 dependence. Also note that this is not a kind of nuclear electron spin flip-flop process. It's a different process. Flip-flops are prohibited at these magnetic fields because there is a huge mismatch of Zeeman energy between the electron spin and the nuclear spin. And so altogether we can fit this together, this joint law, and get a very good agreement. If we look at the fast axis, this is now rotating the sample back along the x direction, and that direction still agrees fairly well with the spin orbit mechanism, but one can see how the kind of gap here closes and how the mechanism becomes more isotropic at lower fields. And so I'd like to point out that this longest T1 times corresponding to rates of order of 1 over 100 here are actually almost a minute plus minus 15 seconds. So it's extremely long spin relaxation time. And also, by changing the magnetic field from about half a Tesla to 14 Tesla, we're changing the spin relaxation time by about 6 orders of magnitude. So this is going up to above 10 kilohertz and below close to 10 millihertz here. Right, so how come this wasn't already seen earlier? Well, one difference here is, first of all, the electrons are a little bit more confined. That helps to make the spin relaxation rate slower. And also, the temperature is lower. And so this was possible by doing kind of good filtering of these electrons. So let me skip this and kind of end up here. So if we look at the anisotropy, the ratio of the relaxation rate with the field applied along the x direction or the y direction, then this high fields, this was around this value of 15, and it goes to 1 at low field. So again, this is the regime where spin orbit relaxation is dominant, and at low field it becomes hyperfine relaxation. And this b to the 3, which is also consistent with the experiment. So this is also a work in progress. We're just in the process of writing this up, and this work was done by Leon Comensind and Liuchi Yu in Basel, and I'd like to thank Peter Stano and Daniel Loss for the theory of this, as well as Art Gossard and Jeremy Zimmerman for the electron gas. So let me summarize this. We basically have unprecedented command of the dot, and that includes not only shaping the dot with gate voltages, but we developed this new kind of spectroscopy with the in-plane magnetic field that allows us to do kind of a 3D model that includes also the orientation of the orbitals, and this allows us to get a good handle on the spin orbit parameters. We have discovered or found in experiment this long predicted hyperfine mechanism of spin relaxation, which is not flip-flops, but actually is just mixing the spin states with the Overhauser fields, and we get a T1 time of around 1 minute at 0.6 Tesla and 60 millikelvin. So I'd like to also note that just a month or so ago, there was a paper by Watson and Michelle Simmons and co-workers that reported 30-second T1 time, but in silicon. So this was silicon with phosphorus donors, just a few atom phosphorus donors, and they get 30 seconds. The mechanism is completely different there because it's silicon, it's very weak spin-orbit coupling, it's more the direction of mixing of heavy hole and light holes and so on. But anyway, this is also a very long time. So with that, I'd like to thank you for your attention.
Thank you. So we have time for a couple questions.